Okay, fractals were cool, but you may be wondering what those recursive definitions are useful for, except for drawing mountains and plants and redefining sums in a weird way. They're actually used to define a lot of objects, and the reason that you want to use them to define those objects as opposed to just, have a verbal description is because such definitions allow you to check whether something is indeed a properly defined object of the kind, say, your program expects as an input. So in general, you can define not only sequences, functions, and so on and so forth. You can define very general things such as sets. And this is what you see most often when you're dealing with recursive definition of things in computer science. You define sets and you also define like structures, like data structures. So here are some examples of definitions of sets, recursive definitions. And by the way, hopefully you didn't get an impression that there is only one way of doing things. A lot of times you can define the same sequence in different ways, and with sets it's even more so. You could define the same set many different ways. So here is an example. So let's look at a set of all binary strings, that is all sequences of zeros and ones in whatever order, finite sequences with 0 or more elements. Here is one way you can describe what the set looks like. You could say that an empty string is in the set of all binary strings. It's actually a set of all strings over whatever alphabet you choose. And for the recursion, if some string is already in a set, then if you take the string and put a 0 at the end, you get something in the set. If you take a string and put a 1 in a set and put 1 at the end, you again end up with something that belongs to the set of binary strings. So for example, if you already generate the string 0, 1, 1, and you know it belongs to your set of binary string, then that immediately tells you that the string 0, 1, 1, 0 and the string 0, 1, 1, 1 are also in the set of your binary strings. Here is another way to define the set of all possible binary strings, finite length binary strings. We could start with a different basis, putting not just an empty string in it, but also a string containing just 1, 0 and a string containing just 1, 1. And now we could get away with a single rule and not two. We just say if there are two things in our set, then their concatenation, that is, you write the first one followed by the second one, is also in a set. So since a 0 is there and a 1 is there, that means that in particular you could always take a string from the set and write a 0 at the end or a 1 at the end. So note that you could have the basis from the second definition and still use the rule from the first and it would work. But in order for the rule from the second work, you really need the basis from the second. You really need to have a 0 and 1 there. And one more important thing about recursively defining sets, or in general recursive definition, which often goes unsaid, is that you are assuming that S does not contain anything except for things that you put in there. So if something has not been in the basis or generated from the basis by applying the rules of the recursion, it doesn't belong to the set S. You cannot have, for example, if you have a definition, the definition from a set of binary string, a symbol 2 in there. There is no step in the process that would put 2 in your set. So let's define something else which you're going to see a lot in your later courses. So in computer science, a tree is a special kind of a graph. So remember when we talked about relations, we talked about graphs of the relations where we had vertices, nodes, and then we were connecting them by lines. Usually the lines were pointing in some direction, sometimes in both directions. Well, if your relation is symmetric, then rather than writing two lines pointing both ways, you could just write one line between the nodes without arrows. And this will make a graph undirected. So if you have a graph directed or undirected, it may have a cycle. And a cycle means that if you're standing in a node on a cycle in a tree, and you start sort of walking along the edges, then if you're walking along the edges of the cycle, you will eventually come back to the same node. It works for both directed graphs and undirected graphs. So this is kind of like saying that a vertex, the pair vertex and this vertex again, XX, belong to the transitive closure of a graph when the new graph is not reflexive. That's what it means to be a cycle. So a tree is a special kind of graph that does not have cycles. And when you don't have cycles, a lot of things become much easier, because you know that if you're walking through the graph, you're not going to start going around in circles unless you start backtracking. In order not to backtrack, you need to keep track of a direction where you are going, and this introduces the notion of a rooted tree. So what's so before we go there, let's just define what a tree is by using recursive definition, even before we get to the rooted tree. So a basis contains just a single vertex, and for now the names are kind of arbitrary, but a vertex is a tree. Well, technically empty tree is also a tree, but let's just say that the basis is a single vertex because empty tree is kind of boring. And recursion, again, there are other definitions, but one possible definition is if you have a tree and you have a vertex, then you can get a new tree by taking that vertex that's not, if you have a tree and a vertex that's not in the tree, you could get a new tree by taking the tree that you have and the vertex you have and just drawing an edge from that new vertex to any vertex in your original tree. So for example, here I have a vertex, I get another vertex and I connect it to the first one by an edge, I get another vertex, and really doesn't matter where I connect it, I will get a tree. And every time to build bigger and bigger tree, I pick a vertex that's not in the original one and I connect it to something that's already in the tree. You could actually prove that this process would give you all possible trees. Okay, so other things that you could define using recursive definitions is things like arithmetic expression. And this is very useful when you're writing a program that expects an input of a certain kind, like an arithmetic expression or formula, and before it starts, for example, trying to compute the value of the formula, it needs to check that the input that it got is correct. Because if you get something like 5 times plus minus 3, you really wouldn't know how to calculate this. It doesn't make sense. So instead you want to take an arithmetic expression and you want to take your input and the very least make sure that it's a proper arithmetic expression before doing anything else. But how would you describe a proper arithmetic expression, well-formed arithmetic expression computationally? Well, here again, you could use the recursive definition of a set of all well-formed proper arithmetic expression, a set of all inputs in which your program would do whatever it needs to do. So, for example, you could define it like this. If it's a number or a variable, then all is good, it's a proper arithmetic expression. And now, and by the way, this definition is a little simplistic, we'll give a better one soon, but let's say you have two arithmetic expressions, and if you put an arithmetic expression in parentheses, you get an arithmetic expression. And if you add two arithmetic expressions, subtract one from the other, multiply them or divide them, you still get an arithmetic expression. So this is a very kind of basic definition that doesn't capture a lot of things. For example, it doesn't capture the order of evaluation, it doesn't check that you're not dividing by b, it doesn't even check that you're not doing multiple parentheses on the same thing, which are allowed here but kind of look weird. But it does allow you to check that something is an arithmetic expression by kind of checking that you could build an arithmetic expression by using the rules. Of course, when you're doing it, you will go the other way, you will break things down, but let's just first show how to build it. So for example, if you have an expression 40 minus x plus 1 times 7, this is a well-formed arithmetic expression because it consists of 40x, 1 and 7, which are all in the basis, they are numbers variables. Then out of x and 1 you could build x plus 1, you could put x plus 1 in parentheses, you could multiply x plus 1 by 7, and you could subtract the result from 40. Or alternatively, you could go the other way and you could get 40 and so on. So again, this is kind of a very basic way of doing it. It doesn't capture order of evaluation, other thing, but we'll spend the whole next lecture talking about capturing things like that. So let's do another example which is very similar to arithmetic expressions, and this is something that you've seen in one of the earlier lectures, but at that time we didn't talk about it as recursive definitions. We just say that variable is a formula, a constant is true, a constant false is a formula, and if you have a propositional formula, you could put it in parentheses, you could put negation in front, and you could take and, or, implication, and biconditional, and of two formulas, and end up with a formula. And for the predicate logic, the same thing, except now you also change the base case. It's actually a lot more complicated if you want to introduce functions, but at the very least your base case should be predicates that take the proper inputs. And for the recursion, it's the same thing, except now you also have the rules for adding quantifiers. And again, as before, only the things that can be built using those rules are the well-formed predicate formula. For example, often on the exams, people write things like likes of x, comma, y plus x, and that's totally not a well-formed predicate logic formula, because likes takes two people, y and x is not a person, and actually you cannot say and with two people and get something meaningful, like John and Jim. Is it a person? Is it a yes? Is it a no? And also here there is a comma between the two likes, which I wouldn't know how to interpret, or more, well, you may not care that I don't know how to interpret it, but if you're writing a program that takes in a formula, your program wouldn't know how to interpret it because it doesn't fit the recursive definition of a predicate logic formula. Okay, so now that we are talking about building things, I mentioned the order of operation, here is the puzzle for next time. Here are the two sentences. One of them is time flies like an arrow, another one is fruit flies like an apple. The middle three words are all the same. The first word is different and the last word is different. Not too different, but a little different. Question to you. Are those sentences, would you consider those sentences having the same structure? They do look very similar, but would you really consider them to have the same structure? And if not, how would you describe the difference between how those two sentences are built?